Okay, so yesterday I didn't go through this last part, which is the spectrum calculation. But anyways, there's not much of magic there. From that one, we start by setting up the sampling rate. For example, 11,025 hertz, which is the quarter of the CD quality sampling rate. It's good for voice like this. Yeah, and then one way of producing a time vector would be to start, for example, from 0 seconds and then put the 1 over sampling rate as a step size, and well, for example, 1 second long sample. That's a one way of doing it. So 1 second long sample at sampling rate of fs. Okay, good. So next I will just generate a sinusoid sample, for example, like this. My signal x is 0.4 times sine of 2 times pi times 440 hertz, note A, times the time vector, 2 pi ft. So 440 hertz equals note A. There, which sounds like this. Again, I don't have of course, I don't have the sounds coming up. Mixer, no. Huh. Playback device speakers. Okay, default. Yeah, that snap sound. Oh, that's an artifact. There shouldn't be one, but actually I'm starting with the a sound directly, not fading it in. Then basically that's what happens. But anyway, so that's my sound sample, and I can then add some noise to it. SSNN equals SS plus, say 0.01 times rand n and size of TT. So this one gives me noise where the amplitude is 0.01. Not much of noise, but anyways, just to put something. Oops. What? What is this one? What's oh not SS. I created XX. There we go. So still sounds about the same. Okay, let's do some spectral analysis for this one and calculate the Fourier transformation. Fourier transformation, and basically fast, meaning that fast Fourier transformation requires 2 to the power of n samples there. And now I have 11,000 samples, and the closest power of 2 would be 2 to the power of 13, right? So I'll take only that subsample and just calculate the Fourier transformation for that one. That's the biggest number without adding any extra zeros at the end of the data. So basically, I'll take the okay. Let's see. I take the sub sample SSNN from the first value to the power of 13 values. So using those indexes. Actually, the on the exercise, you need to figure out how to calculate the what is the last 2,000 samples of that big sample. And well, there's the size of TT gives the two-dimensional vector of the okay, good. So now I have the sub SS, and I can then calculate the Fourier transformation of my sub SS. I will just call it fxx fft of sub SS. So this is the complex Fourier transformation, and by itself it doesn't really have any other meaning that it's it basically just the same signal, but now it's represented in frequency space instead of the time space. So it's inverse time space. Okay, frequency space. Right. To calculate the power of it, actually what we need to do is to take the this number and multiply each element with the complex conjugate of that one. So basically we are calculating the norm of fxx. So, and that's actually the power spectrum without scaling currently, no scaling, arbitrary units. But anyways, it's related, directly proportional to the power. Okay. We could already start plotting it, and well, I'll just plot it for fun to see what it looks like. Okay, it actually looks like that. And why? Okay, there are two peaks instead of one. Okay, two peaks, one here, another here. Although there's only one frequency. Well, the mapping of this is a little bit awkward, but not really awkward. It's the frequency. Well, the x-axis, the horizontal axis, is showing the frequency or the frequency index currently. And it starts from 0 frequency, which is DC, and the last point there is the basically back the 2 pi. When you think of the this z-plane and unit circle on it, we already noticed, okay, if we have the angular frequency omega, there we have a to j omega is right there on the unit circle. But, well, basically when you go to this point, you have the physical frequency is fs over 2. So the Nyquist frequency is here. And when you just continue, you get back to the, well, the zero frequency is also n times sampling rate. So it repeats itself infinitely. And basically this lower half of the spectrum is just a mirror image of the upper half when you're talking about the power spectrum. So the only part that we are really interested are the first half of the data points. And now this mapping, that's linear mapping from 0 to fs. So we can also calculate what is the corresponding index value, what it corresponds as frequency, simply by saying, okay, 2 pi is the last one, and we start from 0 to, well, n minus 1. N is the, well, not that one, okay, k times. That's a number of samples, minus 1, because actually I want only n numbers there, and then divided by n. Okay, that'll be, well, not ff, but omega. To get the ff, which is the, or f, the real frequency, we had actually the omega divided by 2 pi times fs, which is simply, well, the whole axis there is basically 0 to n minus 1 divided by n times fs. So practically we have the delta f, meaning the distance between two spectral components, which is the spectral resolution, is actually fs divided by n. Well, that makes a lot of sense. We have now 8,196 points on spectrum, and the whole range is fs. So the spectral resolution of the spectrum is the fs over n. Okay, so a lot of stuff happens there. So delta f equals fs divided by length of, well, pxx practically. This is the spectral resolution of our calculations. About a little bit more than 1 hertz spectral resolution. And we had exactly 440 hertz. It doesn't actually, this one already says that, okay, the spectrum has been divided at least into 2 different bins. Okay, but first things first, the whole range of the frequencies is now, well, let's see, delta f times 0 to length of pxx minus 1. Okay, that's the whole range, whole frequency range. And now we can plot the same stuff again, ff, pxx. And now we have physical frequencies here. So now the x-axis is actually in hertz. But we still have, too many points there. But we can always fix that by saying, okay, nn equals. So our region of interest is from 1 to, okay, length of pxx divided by 2, okay, plus 1. Where does plus 1 actually comes from? From the indexing. So basically, we start from 0 frequency, which is at the index 1. And I also want to have the exact fs over 2 there. Good morning. Exactly the fx over 2 frequency also marked. So the last point is actually showing the power of the spectrum at highest possible sampling rate. Highest possible frequency. Whew. Okay, so that's the full region of interest for us. And we can plot it again. Let's plot FNN PXNN. Good morning. Okay, so that's the whole stuff. So now we have that one peak there at 440 Hertz, and then rest of the spectrum. You probably remember that I added some noise, and now it looks like the noise floor is at 0. That's because this has a really weird vertical axis. Well, actually, for human ear, also the horizontal axis is off. Frequency should be showing on logarithmic scale. But what is more important, we should show the this power always in decibels. Okay, power in decibels. Remember that one, dBpxx. We made the this power spectrum by making just multiplying the Fourier transformation of signal, the complex conjugate. So basically, this is already the power, and well, unscaled power in dB would be 10 times log of 10, and then just simply pxx. This is well, unreferenced power. But anyways, in power, the most important part of the power is basically how they relate. The spectral components are relating to each other. So we can always fix the reference level somewhere and say, okay, this is our reference. All right, so we could fix it, for example, at the rate where the least significant bit is. I'm not doing it though, but you can. So this is the power in dB on referenced. All right, now we can plot again. dBpxx. There we go. Now we can see also the noise part. Yep. Does it make sense? My noise amplitude was 0.01. So noise power should be somewhere around, let's see, 0.01 would be 80 dB. Maybe it makes sense. Actually, we have a concentrated power of our signal at that 440 Hertz, and then this noise part actually has the white. Well, it's basically white noise, so spectrally flat distribution. So in principle, we should integrate this noise floor and then compare it to the integrated power of the signal. Okay, but anyhow, that one shows when you have the basically the decibels, plot the spectrum in decibels. You can see basically where is the signal and where is the noise. Okay, so noise is that white speckle there, and then there's that 440 hertz. Let's take a closer look at that one. Is it really at 440 hertz? I'll open that. I didn't want to open that. I need to open Zoom. Okay, let's see how close to 440 hertz is this one. Well, it's pretty close actually. Exactly 440. No, it's not exactly. It cannot be. No, it's not. It's a little bit off. Well, it doesn't fit exactly on that 1.34 hertz. The spectral resolution. All right, so that's how the spectrum looks like. Good. One thing, the frequency shows up as a peak on the spectrum. Good. But this is a little bit boring picture because our signal is not changing, so it's just a constant frequency. But if we had a varying frequency, then basically there's a problem. How do I know when the different frequency starts? Let me add a little bit of data into this one. So for example, I could take SSNN, okay, or actually can add some noise. Let me change the noise so that it starts. I will add to the original, I will add, oops, escape. Oh, okay. Let's see. SS2 equals 0.2 times sine of 2 times pi times, say, 440 times 3. So it's the third harmonic times t. Okay. Add third harmonic. But not from the beginning. I want to add that one later on. Then I calculate the power spectrum again. Then I calculate the decibels for power spectrum again. And then I plot it again. Okay, so this is what it looks like when we start. Whoa, Why it didn't show up in here? Why it did not show up in here for PXX? Oh, I should have calculated also the FXX. Then PXX. Then decibels. Then plot it. Okay, now we have the third harmonic. And it sounds like, there. This does not carry information about that. So it's missing where the other peak actually starts. That's why we also have a tool called spectrogram. Spectrogram gives information about also about the not just the frequencies and the power, but also the time information. So spectrogram actually have the frequency on the vertical axis and time on horizontal axis, because, well, horizontal time is always horizontal, right? And then the vertical axis is for frequency, where to put this this information about the power. Then that's color coded. But let me calculate the spectrogram of my signal SSNN. I do the whole signal now. I don't want to just take the 2 to the power something. Then window size, meaning how many samples you take from that big sample. So basically what a spectrogram does is it goes through the signal step by step. So if we have a full signal here, takes a region of interest, which is the window size, calculates a spectrum, and color codes it as one block here. Then it moves on to the next window. Okay. And the window size then, if you think of how many pixels you want here, you probably want at least, say, around 100 pixels. This is an image. This is an image, actually. It's not really any big scientific thing that you need to exactly check what are these frequencies. That's where you calculate individual spectrum. Then you can go into fine details. This is a big picture. It's kind of map of what happens. And then you need to have, say, roughly 100 or more pixels here. But, okay, you also have the negative frequency as well on the top of that one. So it means that the window should be, say, roughly more than 200. Since only half of those will give you the information about the 0 to Nyquist frequency. So 128 is a good number, since it's, n to the power something. The 2 to the power something. Then number overlapping bins. Unless otherwise noted, use the half of the window size. So go, unless you really want to have see the say, well, it doesn't really show anything, but this basically just gives you how smoothly this picture is forming. It does not give you any more resolution or anything like that on time-wise, but basically, if you overlap those more and more, then you start going with the smoother transitions. Here, if you go in big steps, then there'll be discontinuities here. But it's only about how to make this graph. Half of that would be 64. Then, number of values in Fourier transformation. I don't see any other reason, other number to put there. Why I put it 228, nobody tells me anything. 256, sorry, 128. Yeah, more than 200 was the first one. Okay, the next parameter is the number of points in Fourier transformation. Use the window width. I don't see any other, reasonable values. If you put it less than the window width, you're not using the whole data here. If you put it more than the window width, you are just padding zeros to the end of the data. It doesn't improve it doesn't really improve the quality of your analysis here. It's just artificial zeros that you will put there. It doesn't add any information. But yes, you get higher spectral resolution. For what? I don't know. This is just an image. So 256 is a good number. Then sampling rate. If you know the sampling rate, yes, use that one. Okay, then I need also another parameter here, which is y-axis. Why I have y-axis here? Because of the spectrogram function is written by morons. Seriously, I will show you what happens if I don't put it there. Just to make a point. This is not spectrogram. Have you ever heard of any graph where your time starts from bottom and grows up? What? I can understand the water flow, which is opposite. Then basically time flows like this one, and then these spectral components will appear there. That will be waterfall kind of. But this is, mathematicians' view. They don't care about the, reality. So never give me any of those kind of plots. Always use y-axis here. Now it makes sense. So, okay, so we have this time from 0 to 1000 milliseconds, frequency from 0 to Nyquist frequency. The spectral power actually divided by the spectral resolution. So basically, this will be the watts per hertz. Okay, meaning that if you integrate over the frequency range, you get the total power in watts. Makes sense. So, okay, we have roughly, say, minus 70 dB noise floor, and then we have about 30 dB. 30 dB the signal strength. Okay, good. So that's the spectrogram. Then the individual spectrum was just calculate the Fourier transformation of the signal. So basically, if you have a signal that varies, then the spectrogram is the correct way of doing the analysis. If that is signal is so that you really want to just check what are the spectral components there, then maybe in average, then you maybe want to make the just individual spectrum. Good. So that's the part I didn't go through yesterday.